Well, we have an absolutely super programme this evening of great variety and interest, and it's my pleasure to introduce the first speaker, Dr. Rebekah Higgitt from the University of Kent, to give a diary talk entitled Expeditionary Astronomers, the 1769 Transit of Venus and British Voyages of Scientific Exploration. Rebekah.
Thank you very much for inviting me to speak about an anniversary. I should say the image on the first slide here is in fact a little later. It's from the 1780s, the third circumnavigation by Captain James Cook, showing the ship's resolution and discovery in the Society Islands. I've included it because in the background you may just about be able to make out the camp on land, where the more triangular shaped things you might be able to see, or I'll have to direct you to a better image of this online. It's in the collections of the National Maritime Museum. Those are probably observing tents set up. So they mark the location of some expeditionary astronomers and, of course, the equipment, which is what the tents are keeping sheltered from the elements. So this year saw the 250th anniversary of the 1769 Transit of Venus. It was on the 3rd of June, 1769. For most British people, the one we think about, the observation of the many that occurred in that year, were those made by the then Lieutenant James Cook from Tahiti. There is an image of the observing compound at Tahiti and also the observations that Cook and the astronomer Charles Greene made, including their discovery of the problems of the black drop effect. So he sailed to Tahiti, Cook and Greene and the rest of the crew on the Endeavour, and from there, of course, they went on to explore the Southern Pacific. So what this week, in fact, sees the anniversary of 250th anniversary is of that ship reaching New Zealand, and you may have been reading in the newspapers about the replica of the Endeavour that's currently going around New Zealand and provoking understandably complex reactions from people there, particularly Maori people who recall the deaths that resulted immediately from that sort of euphemistically put encounter, and also the resulting loss of sovereignty that followed. So an important reminder that this is not just an astronomical expedition. But on the Transit of Venus itself, I just want to go briefly through the why this happened, what was needed to make sure that it did, and what was the longer-term impact? So I'm talking about other voyages beyond 1769 as well. This map of the transit in that year by Jérôme Lalande reminds us of several things. One, that you need to travel to observe these often because where the visibility is best might not be where you happen to be living. Two, prediction and preparation planning are obviously required to know that this is going to happen and to know how you're going to get there and what you're going to do. And also that it was very much an international effort and indeed very much a French one as well. So I'm talking about the British context, but we shouldn't forget it certainly wasn't them alone. And indeed, they were somewhat behind the French. Transits of Venus, as I'm sure you all know, occur in pairs over a century apart. So there were transits in 1730s, in the 1630s, 1760s, 1874 and 82, and then most recently 2004 and 12. The aim, of course, was to use this rare conjunction of Venus and the Sun in order to observe solar parallax. And the 18th century observations are important because this was what they had in mind, the understanding that you needed to travel to make this observation and to make observations from at least two different places so that you could get the parallax effect, and so establish the distance between the Earth and the Sun, or the astronomical unit as it's now known. So, why? Well, many reasons. One, it's nice to know. I'm sure all of you feel somehow you know more by knowing how far we are from the Sun. But, you know, yes, nice to know, but does that get you the kind of funding that you need to carry out the kinds of expeditions that happened? Well, probably not. Certainly that you can sell the kind of glory of knowing, and this is sublime heavenly knowledge to understand our place in the heavens. And of course, the glory of being able to know this, to show that you have the skill and the expertise and indeed the navies that can take you around the world and so on. So that's the kind of thing that might get your your Louis and your Georges kind of interested and willing to fund what's going on, demonstrating the prowess of their nations. So international competition is certainly an important driver for what's going on here. As I say, the British wanted to catch up with the French. They certainly wanted not to be seen to be doing nothing when their competitors were doing that. The ultimate project absolutely depended on collaboration between observers. The numbers that were crunched together to get a figure came from around the world, but certainly competition is in there as well. And imperial competition, we should remember, is really what's going on there. The ambitious imperial nations, recalling that France and Britain were at war, both North America and around the Pacific, over imperial control and influence at this time. Showing that you can get to these parts of the world, that you can stake a claim to them, that you can be seen to be acting in an effective way overseas, are all very important to be seen to be doing by your competitors. And of course, Cook was to try and locate new land after the observations in Tahiti. He was told to do that, to observe the potential usefulness of the natural resources that were found, and quoting from his so-called secret instructions, the genius, temper, disposition and number of the natives, and to try and come to agreements and essentially stake claim to the land for the king. Certainly, the extent to which they could claim that these observations of the transit of Venus would improve knowledge of astronomy generally and the accuracy of astronomical tables in particular was an important part of the argument, particularly among astronomers. But astronomy is a good thing, it was understood, particularly because of the way in which you could connect it to navigation. So the thing that you're selling to your governments and your navies and your monarchs is the idea that improving astronomy, so plugging real data or in terms of the distances of the solar system, the masses of the sun and the planets into your calculations rather than just relative ones, would improve astronomical tables and would improve navigation as a result. And that would be useful for your navies, for surveying, so for Empire 2. So a very broad sense of navigation might be added into that, in the sense of which making these observations and also the kinds of exploratory voyages that were added on as well, give a potential for increasing trade, finding new trade routes, more commerce and so on. So this is very much part of the sales pitch as well. What was needed to make these kinds of observations? Certainly instruments. So this quotation goes back to 1760. This is the immediate response from James Bradley, the Astronomer Royal at the time, at the Royal Society, when they had heard that the French were planning expeditions. A letter from Joseph-Nicolas Delisle came in and was read, and they played catch-up rather quickly. And Bradley was asked what sort of thing we would need. He says this. He mentions the sort of minimum requirements for an astronomical expedition and what is the essential basis for what comes after all, as we'll see, expands massively from this. But a telescope for which you can observe the particular phenomena that you're interested in here. He talks about Dollond's micrometer, also known as a heliometer by J. Dolland and Son, through which you can make very accurate measurements of, say, the solar disk or, of course, of Venus travelling across that. He also talks about a quadrant and refracting telescope and a clock in order to support the kind of positional measurements that are needed to establish where you're observing from, the precise longitude and latitude and time of your observing position, so that you can then make those comparative calculations between the different observing points and establish parallax. Those, of course, require a long setup, as it were. You need a lot of observation in order to set the going of your clock to really get a good fix on that. So we're talking not something mobile, but something that is fixed for a period of time in order to do it well. You also need money, of course, and in 1761 they did rapidly manage to get two expeditions going and succeeded in getting support from George III. He offered £800 each to two expeditions that the Royal Society organised, and they travelled on merchant and naval ships. One went to St. Helena, the other one was aiming for Sumatra, but only got as far as Cape Town. That being because it was in the middle of the 7 Years' War. So it's one of those great trials and tribulations stories you can follow up with. It's not Mason and Dixon, isn't it? I've got that wrong. Someone can check that. Dixon, certainly. Oh, no, maybe it was. I can't remember. Anyway, there's so many observers and so many expeditions. I get confused about who's who sometimes. So they only got that far, but they did make an observation. Neville Maskelyne, not yet Astronomer Royal, and Robert Waddington failed. They met with clouds instead. The aim was certainly to do something a little more impressive by everyone. There were unexpected results and difficulties in 1761. So there was another push for 1769. More funding was secured by the British, from the King and from the Admiralty as well, and the Royal Society again, as well also the Board of Longitude playing organisational roles in this. So there were actually 5 expeditions, but the one we really remember, as say, is the Tahiti one, which you can see got quite a lot of funding in order to make it happen. And the naval interest, of course, very much also being in that further set of observations and explorations that would happen after the transit. So here we have the observing compound in Tahiti again, and the suite of instruments that would be set up there. It was called Fort Venus, which again is a nice reminder that this was something that was military as well as astronomical. They have this military fort. It's full of naval officers. It's also Royal Marines are there on board the ship, and here they have their cannon, they have their guns. So the observers, sorry about this picture, there is no portrait of Charles Greene, and I was going to put in those observations again, and then I came across this on Pinterest, which is a learning resource from Australia that has him and other figures from the story for children to sort of work out who's who saw what, I think is the name of the game that they play. How do we learn about history? But anyway, so this is possibly Charles Greene, and he is the astronomer observer who was appointed by the Board of Longitude and the Royal Society to make these observations. He was once a teacher himself, but then assistant at the Royal Observatory in Greenwich under James Bradley. He was an expeditionary astronomer on one occasion before this. He accompanied and was assistant to Maskelyne when he was trialling 3 different methods of finding longitude at sea for the Board of Longitude in 1763-4. Greene made those observations that you've seen images of, then also sailed on, reached New Zealand and Australia, making observations on land there to fix positions. He was helping to navigate through the new astronomical methods. The Nautical Almanac was newly available just in time to go on this voyage, to be trialled at a distance and on board ship to see how well it was working, and to see if he could teach other officers to use it as well. That was something he was very much told to do. So he was supplied by the Royal Society with a whole range of instruments for carrying out survey, observations of geomagnetism, metrology, hydrography, and so on. Sadly, Greene died in Batavia in 1771 and never returned home. James Cook was Greene's assistant in the astronomical role. He was obviously commander of the expedition, but assistant as an astronomer. This portrait is from 1775, and it shows him after his second voyage, when his reputation is very much secure. He'd just been made captain at that point. And also to sort of contrast, so while Greene's story tells us about the mathematical and observational skills that developed in London and in connection with places like the Royal Observatory, its production of the Nautical Almanac that required a lot of computational labour by mathematicians, and most of the transit of Venus observers to those other expeditions were in that sort of camp. Cook tells us that obviously these sort of skills could also be an advantage in gaining recognition in the Navy, and all the more so because of the results of his voyages. So as Cook's fame rose and the kinds of results that they achieved, that gave more interest from the Navy into the kinds of skills and instruments that were being used on them. Cook himself had been a master of a naval ship initially, and he gained, in that role, his navigational and surveying experience in North American waters during the 7 Years' War, also there afterwards. So he had a very practical training in mathematics and astronomy, but clearly also leisure to develop his interests and to assert his knowledge as well, because on the 5th of August 1766, when he was out there, he found time to observe a solar eclipse and then to briefly write it up and send his observations to the Royal Society. So the Navy had got to hear of Cook and his skills, but so too had the Royal Society, which sort of explains why he was accepted not just as commander of the expedition, but also as an astronomical observer for it. He proved capable of making the same range, really, of observations and calculations as Greene did. He made use of the lunar distance method and found it a good improvement, as well as also doing his running surveys, precision charting, and so on. So the Endeavour expedition was a great success, and within a year of his return, Cook was to be sent out again on another one. That voyage certainly included Cook and other skilled navigators and surveyors. It was also to have, again, like the Endeavour voyage, naturalists on board and artists. But there was no specific astronomical observation behind the motivation of this second voyage. So it might have lacked more specialist astronomical expertise had Neville Maskelyne, now Astronomer Royal, not intervened at a rather crucial moment. So he took the initiative in 1771, writing to Lord Sandwich, who was then First Lord of the Admiralty and also therefore a Commissioner of Longitude, saying that that voyage, the second circumnavigation of Cook, which had 2 ships going out instead of 1, may be rendered, he said, more serviceable to the improvement of geography and navigation than it can otherwise be if the ship is furnished with astronomical instruments, as this board of longitude hath the disposal of, or can obtain the use of from the Royal Society. And also some of the longitude watches, and above all, if a proper person could be sent out to make use of those instruments and teach the officers on board the ship the method of finding the longitude. So this was a great opportunity to do several things, Maskelyne saw. One of them was to increase the number of officers in the Navy who had a sense of how to pursue the lunar distance method and to use the nautical almanac, which of course is a product of the observations at Greenwich in the observatory there, and of Maskelyne and his calculating team who are behind the production of the nautical almanac. So he's certainly looking to spread the use of that. Note also, though, the timekeepers at the Board of Longitude, the ones he meant here were made by Larkham Kendall, which was a copy of Harrison's Sea Watch, and John Arnold. So it's not true to say, in case some of you had read a certain book, that Maskelyne was not interested in promoting timekeeping as a method of finding longitude as well. He saw those things very much working together and wanted to get both of them going and being tested at a distance from home. It was also an opportunity to get an astronomer, someone who knew their stuff, to be fixing positions around the world, making very accurate determinations of longitude on land in order to test your navigation methods. Are they working? In order to provide future fixed points for navigators to find reference to, and then, of course, to provide a basis for further charting and surveying. It was also making use of this suite of instruments that he mentioned, that the Royal Society had gathered from its involvement in all those Transit of Venus expeditions, and which the Board of Longitude had also begun to gather, either as things submitted to them or as things that they were using to test them on their trial voyages too. So the Board of Longitude agreed that Maskelyne could go about doing this, that he could head a committee in order to find 2 observers that could undertake this work on the 2 different ships, and, quote, to prepare a draft of instructions proper for the said persons, and also a list of the necessary instruments. Maskelyne and team selected William Bailey, who had been an assistant at Greenwich and also a Transit of Venus observer, and William Wales, who'd been a nautical almanac computer and also a Transit of Venus observer as well. In terms of the instruments, the instructions, the personnel, all overseen by Maskelyne, this voyage does certainly follow in the mould of what had happened in the 1769 Endeavour voyage. In terms of inserting astronomers and the expectations of precision, and particularly precision instruments as well, onto what was otherwise purely a naval voyage of exploration that lacked this kind of primary astronomical purpose, or the initiative of the Royal Society, it set the pattern for the future, I would argue. This from the minutes of, you don't need to read this in detail, just go, ooh, that's a lot of instruments. So this is from the minutes of the Board of Longitude, and it's a list of the instruments that they would loan or that were being borrowed from the Royal Society or that would be purchased specially for this voyage. A few more things added in as well, but we can see this, I think, as defining the pattern. And there are a whole sequence, as I'll show you in a minute, of other lists that Maskelyne drew up for other voyages that very much match this. Sometimes with things added in that were experimental, but there is a very clear suite of instruments that define precision exploration of this sort. Next meeting, they added a few more things, another clock, a couple of pairs of globes, some zodiac maps, and also something that they never should forget was the copies of the Nautical Almanac and requisite tables that had to be used alongside that. 12 copies, no less, of each year that they could get hold of up to 1775 for this voyage. And we do see these very similar lists coming out again. This one, these are all available now. You're on the Cambridge Digital Library platform, Board of Longitude papers, so you can scrutinise these to your heart's content if you want to. So this is for Cook's third voyage. He had also made up a similar list to support Constantine Phipps's voyage to the North Pole in 1773. Got a list for the Sirius flagship of the First Fleet and George Vancouver's voyage to the Northwest Pacific as well. On many of these lists, we also find the portable tent, the observing tent listed. This was developed by William Bailey for the second of Cook's voyages and echoes what I showed you in the very first image. This is these sort of pyramid structures that house the key instruments. So each of these sets of instruments also goes along with the observer, and here I've listed them sort of over that whole second half of the 18th century. Those in red are ones who are associated with the Nautical Almanac or Greenwich Observatory, so very closely with Maskelyne. Those in green are naval or military officers, but often had other connections to these individuals as well. So this tent reminds us that the bonus of making expeditions by ship is you can fit a lot of equipment on ships. You don't travel light. If we compare this with exploration of the interior of Africa, for example, you're not carrying, kind of regulator clocks and things like that. You're making do with a pocket watch. But it also reminds us that they had to stop. They had to set up on land to achieve the kind of precision that they were aiming at. These men, as I've pointed out, were all encouraged to teach and to share their knowledge and to get other members of the ship's crew to use the kind of paper technologies and instrument technologies and the new techniques. And we can begin to trace lineages from these people on board trying to teach and demonstrate, and some of those who were travelling with them. So people like Vancouver and Bligh certainly learned from Cook, but they also learned from Greene and from Wales. Some of them, Wales, Bailey and Inman, became teachers or professors at naval colleges. So again, very much part of the pushing of teaching and of the navigation by timekeepers and lunars, of effective surveying and so on. And increasingly, the Navy could do this itself without their input. We find they begin to be able to supply the same kinds of instruments and the same extent, the same precision, and so on. So there was a hiatus sort of after this when we got the Napoleonic Wars going on. But again, after those finished, there's a new push, particularly exploration of the Arctic from 1818. The Board of Longitude is involved with that too, supplying instruments and observers in the same way. But after the board dissolves in the 1820s, its functions are very much taken on by the Navy. We have now a hydrographic office. There are the naval colleges as sort of repositories of expertise as well. So just to finish, by the 1830s, when we have precision survey voyages like that of the Chanticleer or the Beagle, these are clearly a continuation, but they are very much naval affairs without requiring the kind of lay mathematical and astronomical expertise that we see in the 18th century. The images here are by Owen Stanley, who was trained at the Royal Naval College in the 1820s under Inman. And in the 1830s, he was a midshipman on the HMS Adventure and a commander in the 1840s of HMS Rattlesnake, known for Huxley being on board as a naturalist, but with all of this kind of observation being done by the Navy themselves. So we can see the precision, we can see the instruments, we can see the tents, but note that they're all naval officers. Thank you.
Rebekah, thank you very much indeed. This is open for questions. Yes.
I noticed in the picture of the tent seemed to be a grandfather clock. Now that would seem to be absolutely useless on board ship. So how would you get an accurate time when you're transporting halfway around the world?
Yeah, so a pendulum regulator, and no, absolutely not for use on board ship, hence the whole problem with longitude and trying to find a timekeeper that will work on board ship. So yes, it has to be set up under its tent on land, and you have to be there long enough to make the astronomical observations to establish local time and to check that the clock is working properly. So you need to be set up on land, and whenever the ships did stop long enough, the observer leaps out, sets out his tent, tries to make these observations in time and with sufficient precision.
You have to convert local time to Greenwich Mean Time.
Well, that's what the nautical almanac is for. So you need to know what time it is there, and then your nautical almanac will tell you through your observations what the time is at Greenwich, and then you can work out your longitude. Yeah.
Okay. The clock I liked on your list was the alarm clock,
Yes.
which I think I could do with one of those. Anyway, other questions, please. Yes, please.
Thanks. With regard to the transit of Venus and the solar parallax, a great deal has been made, and to my mind actually overstated, about the difficulties of measuring the parallax itself as an angle because of the black drop effect. But if you are going to measure the linear distance to the sun, you need to know accurately the length of your baseline as well. And it seems to me an interesting question as to how much of the error in the resulting solar distance came from the geographical error in the baseline rather than the astronomical error in measuring the angle of parallax on the sky. Have you any thoughts about that?
No, in terms of doing the numbers and thinking what that was. I think the main problem with the black drop effect was they were all surprised and they weren't expecting it. And they thought that was something they could control in a way that you couldn't necessarily control other things. So it did really mess them up. And they thought photography would solve it in the 19th century, and it didn't. The photography really didn't work either.
Both of the 18th and the 19th century values for the solar parallax were within about 1% of the modern.
I knew someone was going to ask me this. So the figure that they came up with in the 19th century, interestingly, jettisoned what they got from the photography, but added in a weighted way the data from the 18th century. So they didn't chuck that. They came up with 92,702,000 miles plus or minus 53,700. So I'll let someone else do the calculations to how. In 1769, it was more out. It was 95 million odd. So it was rather.
Oh, but that could have been geographical error, because I think Ormsby in Oxford, I think he calculated the value between 8.13 arc seconds or whatever, that is actually very close to the modern value of the parallax, not of the distance.
Yeah. If someone wants to get into the figures and tell me the answer, that would be interesting.
Yes.
Well, it goes back to my original question. I mean, the error in the baseline is because you don't actually know your longitude in Tahiti unless you have an accurate Greenwich Mean Time clock. So, even stellar astro observations, you still need to know the time as relative to Greenwich Mean Time.
But that's what the nautical almanac gives you. It's a very valid way of doing it. And at the time, and long into the 19th century, lunar distances was considered a more accurate, as long as you did them enough, it was a more accurate way of establishing longitude or time at the local site and finding comparative fix than the timekeepers. It's an interesting question. If they had taken any of the, if they'd had the timekeepers available in 1769 rather than 1771, if that would have made a difference.
Last question, Richard.
I should say that the Cook surveys are still considered very good, and that data in some parts of the world is still what we use.
A very enjoyable talk, but with a very embarrassing outcome for me. 30 years ago, I went to Tahiti, and I went to the island of Maria, where there's a bay called Cook Bay, and I naively imagined that was where the measurements were made, but clearly I was wrong. Is that right?
Point Venus is the geographical location, as they called it. I don't know if, I'm afraid, how the two match up. I don't know if anyone else has been there.
Did he not make measurements in more than one? Weren't two teams sent?
Well, they were there quite a long time. There was only one team sent, but I think different observations were made on the day. They weren't right next to each other.
I think we have to thank Rebekah again. That was a super talk. Thank you so much.